Hey guys, so in the previous videos we've seen how we could reduce from 81 constants to 36 constants, and later on, based upon the material properties what I've shown in the second part of the video, we could reduce it further to a different number of constants based on kind of material what we use. For example, for isotropic we only needed two independent constants, as for monoclinic we had to have around 13 constants. So in this video we would be dealing with two topics. The first one is that we would try to check the relations of the engineering constants and the significance what they hold in developing matrices. So we would be mainly taking three engineering constants into consideration: the elastic modulus, the shear modulus, and the Poisson's ratio. So the elastic modulus means is the ratio of stress and strain. When I talk about shear modulus, it's the ratio of shear stress with shear strain, and the Poisson's ratio is the ratio, a negative ratio of the strains. We can represent Poisson's ratio as Vij, wherein it's the negative of the strain in the second component with the respect of strain in the first component, right? So this is a brief summary of what the engineering constants actually hold. Now, if we see, we're taking a relation for the orthotropic material. So the orthotropic material has this matrix as what we've shown in the previous case in the last video and here. So wherein these are our strain components, this is our compliance matrix, and this is our stress components. So we would be trying to develop a relation by taking in different experiments. In the first experiment, we would consider there's only one non-zero stress acting, that is sigma 1. All the other stresses are 0. So you can just barely eliminate all these, and the only thing what you have is sigma 1. So the relation what I would be getting is the strain 1 would be S11 times sigma 1 when you do the matrix multiplication, and all these other terms are multiplied with zeros. So the only term what you have is that S11 times sigma 1, right? Perfect. And we also know that modulus of elasticity E1 is nothing but stress 1 by strain 1. See, here we are developing modulus of elasticity 1 and 2. We're giving names because this is not an isotropic material. Had it been an isotropic material, the modulus of elasticity would be constant throughout or in any plane. But this is an orthotropic material, and hence we have different values of elasticity modulus in different directions. So E1 is nothing but sigma 1 by strain 1, right? So similarly, we can develop strain 1 as the ratio of stress and elasticity modulus of elasticity. So I can write my strain as this, that is nothing but stress by modulus of elasticity. Now if I have to equate both of them, I would be left with S11 is nothing but 1 by E1 because the stress terms get cancelled. Perfect. So far so good. Now in the next part, we would be multiplying S21 with sigma 1, and all these other terms go to 0, right? So sigma strain 2 would be S21 times sigma 1, and we also know that the Poisson's ratio 1 2, as I already told you in here, we would be writing it as, if it's 1 2, we write it as negative of 2 by 1, right? So we write it as strain 2 by 1. So I can write my strain 2 as negative of I just send my strain 1 in there, negative of Poisson's ratio times strain 1. So this is my strain 2. So what I would be doing is I would be equating this term and this term, and I can also elaborate this term further by writing my strain 1 as nothing but stress 1 by modulus of elasticity 1. So if I plug in this value in here, I eliminate my stress terms, and all I'm left with is S21 is nothing but a negative of Poisson's ratio and the modulus of elasticity, right? Now in the third term what we have in here is that we multiply this our strain number 3 would be equivalent to S31 times sigma 1, and all these other terms would be coming to 0. For the next terms we have nothing because all these are already 0, and this would be a last component. So strain 3 would be S31 times sigma 1, and similarly we know that the Poisson's ratio 1 and 3 would be the negative of strain of 3 by strain of 1. We can establish what strain 3 is by sending strain 1 there, and we've got a relation of strain 3. Strain 1 can be written as stress 1 by modulus velocity 1. So I've got my strain 3 term. When I equate this strain 3 term with this, my stresses get cancelled, and all I have is S31 as minus V13 by E1. This is our first case. In the second experiment, we assume that only stress 2 is the non-zero component, and all the other components, be it stress 1, stress 3, and all the other tau 2, 3, tau 3, everything's 0. So when I take it this way, what I would be getting is my strain 2 would be S. My strain 2S would be S22 times sigma 2, because S21 would be multiplied with 0 because strain 1 is 0, right? So S22 when multiplied with sigma 2 gives my E2, and we know that strain 2 is also stress 2 by E2. When I equate both of them, I get S22 as 1 by E2, right? Similarly, my stress 1 would be S12 times sigma 2, right? Because this term and this term are multiplied, right? So I can write it this way. I again use my concept of Poisson's ratio, and I develop a relation for strain 1, right? And when I equate those two terms together, I get S12 as minus V21 by E2. For you to understand this process, and again I'll just cover it in a brief way. So strain 1 is nothing but minus negative Poisson's ratio multiplied with strain 2. Strain 2 can be represented as stress 2 over the modulus of elasticity 2. So I've got my relation for strain 1. When I equate these two together, I'm left with this. So if you're observing, we basically following the same process what we did in here. For example, we got S11 as 1 by E1 when we consider strain 1 and this relation. Similarly, so we got S11 as 1 by E1. Similarly, we got S22 is 1 by E2. We got S21 back in here as minus V12 by E1. And similarly, we're getting S12 as minus V21 by E2. So just that the numbers are changing, but the process, the methodology is same. I can write my S31 as negative of V13 by E1, the same thing what we're plugging in from here. And here, when I talk about 3,2, I just write it as 2,3 by E2. So similarly, you get the same thing when you consider stress 3 as the non-zero component. And one more thing, what the most important factor is that we are considering the matrix as symmetric. That is, I already told you, S12 and S21 both the same back in here in the first video itself. When we had to consider this, we told both of them follow the symmetry. So basically, when I have to equate S21 and S12, what's basically given in here, I plug in the values and I can deduce a relation between the Poisson's ratio. Like I can write the Poisson's ratio 1 to S Poisson's ratio to 1 times E1 by E2, right? So this is an important relation. You can use it while solving problems. Now the third experiment, I consider my stress tau 2 3 as only non-zero component. So what I'm left with is that any of these terms, there's no fourth term in these first three, so nothing comes in here. There's only one fourth term, so I can write gamma 2 3, the fourth term in here, as S44 times tau 2 3, right? So that's the only term I get in here, and S44 can be written as gamma 2 3 by tau 2 3. We know that G, that is the shear modulus, is nothing but shear stress by shear strain, but it's just reciprocal here. We're writing the shear strain with respect to shear stress, so we can write it as 1 by G23. Similarly, S55 would be 1 by G31, and S66 would be 1 by G12. So clubbing all these relations, we can just substitute the values of S11, S12 based on the values what we got here, and we deduce this matrix as in final. So this is the matrix wherein we have the terms of E, G, and Poisson's ratio involved in the relation between the stress and strain. Now, one thing what I would like to tell you is that you use this if it's an tropic matrix, but if I say it's an isotropic matrix, the material properties remain same, so that there wouldn't be any discrimination as E1, E2, and E3. Every E would be the same, every G would be the same, every Poisson's ratio would be the same if it's an isotropic matrix. But had it been it's like a case what we're dealing right now, like an orthotropic matrix, this would be the final relation. Now this is the first part of the video. The second part of the video is that now we go for an assumption called this is a plane stress assumption. Now in this plane stress assumption, what we try to analyze is that we simplify the analysis what we've done here. Okay, now we consider thin sections. Okay, it's not that everything's got three planes. Okay, we neglect an axis because the thickness is very limited, and doing this we make the situation more, less complex, right? So usually what we do is we neglect a plane. So in here we've neglect the z plane, that is the stress sigma z shear stress in the xz plane, and the yz plane as 0. Basically this would be the relation, right? The z would be corresponding to 3, right? So these are the terms which go 0. So if these are the terms which grow 0, that is, if we see this matrix in here, we wouldn't be having any 2 3 or 3 1 or 3 term, right? All we would be having is 1 2 and strain 1, strain 2, and gamma 1 2, right? So in all the other terms which have 2 or 3 involved in it, nullified. Like this thing's got 3, this thing's got 2 and 3, 3 and 3, 3 3 3, all these go 0, and I'm only left with this 2 by 2 matrix and S66, right? This is how my matrix would look like. You might be wondering why isn't there S44 and S55, because see, S44 and S55 correspond to 2 3, right? Because I can write my gamma 2 3 as S44 times tau 2 3, but when there's no gamma 2 3 at all, how would this exist? So barely I've got these 4 terms and this 1 term. So this is a reduced matrix, now what we call it as. Okay, so this is called a reduced matrix, wherein if I have to compare this reduced matrix, let's say strain, this is the reduced compliance matrix, and these are our stress components. Now if I have to completely compare this reduced matrix with the previous matrix what we've seen, we can write S11 S1 by E1, right? And S12 as minus V21 by E2, the same what we have in here. The third term will go 0, and S66 as 1 by G12, right? So we develop a relation, and these are the relations what you can just see in here, right? So similarly we also developed a reduced stiffness matrix, wherein these are our stress components, these are our strain components, these are our strain components, and this is the matrix, right? Wherein Q11 would be E1 over 1 minus V12 times V21. So these are the relations what you can just have a look as. Now I'm just stressing on this point time and again. So if it's an isotropic material, there wouldn't be any discrimination. Every E would be same, every G would be same, and every V would be same. So let's understand with the help of a problem. So here the problem says that an isotropic lamina has E is equal to 100 kilonewton per mm square, and Poisson's ratio V is equal to 0.25, mu is equal to 0.25. Determine the reduced stiffness and compliance matrix. So these are the problems what you might be expecting in your exams. As you've seen, he's given us it's an isotropic lamina, and therefore he's just given one E and one V. There's nothing sort of E1, E2, and E3, right? So we try to deduce the compliance matrix and the stiffness matrix from the relations what we've seen here. The compliance matrix we've seen sorry, compliance matrix का relation यहाँ पे मालूम पड़ा हमें, and this is the compliance matrix wherein we got our S terms, alright. So E1, E2 and E is the same because it's an isotropic material, and S11 and S22 is 1 by E because based on the relation what we've seen here, there's no E1 and E2, just 1 by E. So we will get a value for S11. Similarly, S12 and S21 correspond to minus V by E, so this is the value, and S66 is 1 by G, so this is the value. So when we plug in the values at their respective positions, we get the compliance matrix. As simple as that. Now when I talk about the stiffness matrix is shown in here, the same what we did using here. We get the values of Q11 and Q2 is this, Q66 as G, and Q12 as this. So when we just plug in the values of E, V and G, we get a matrix, and when we plug in with their respective positions, we get Q. So this is all about macromechanical analysis of laminates. For deeper understanding, you can also refer more complicated problems. So that's all from my side. Yeah.